Hey guys, Mr. Rysz here to help you out on the 4.2 notes. So as we go through this, we'll kind of pause. I'm going to make this just a longer video because I have more time right now. But we'll be spending 3 days on this section. So here we go. The goal basically is to be able to graph rational functions. So it sounds easier than it is, but there's a lot of different things that could happen when it comes to rational functions. So we're going to look at that. So first, we're going to look at 3 functions here. Only one of them is considered to be rational, and that's this last one here. But we're going to look to see the difference between the two. Now, I'm just going to pull up Desmos. I think it'd be easier for me to do that here. So Desmos, already got some graphs here. You know what? I'm just going to reload this to get this started nice in the center. So we first got the first equation, f of x equals, actually, I don't need to type that. I can just say x minus 1. That's going to be a red function. We got x minus 1, and then we're going to divide that whole thing by 2. Okay. And then we got x minus 1, and we're going to divide that whole thing by x minus 2. Okay, that made it a completely different equation. So let's see if we can answer these questions here. All right, so graph each function, which we did here. Determine which functions are linear. I would definitely say f and g are linear. All right, find the y-intercept for each one of these functions and the slope if possible. So the y-intercept for the first one is -1. Right? Yeah, the red one is -1. And the slope is, if we look at the red line, it's going up 1 over 1. Okay. So maybe we'll write that down there. My toolbar out here. All right, so f of x, say we'll make a linear. F of x is linear and its slope is equal to 1. And then we'd also probably say that the blue line g of x is also linear and its slope is equal to 1/2. All right. And if we look at that, oh, and the y-intercept, I forgot to put those down. The y-intercept here is at 0, -1/2. And on the other one, the y-intercept is at 0, -1. Okay. So the next question is, what's the effect of f when we divide the x minus 1 by 2? Well, if we look at that, all it did was just lower our points. So all of our points are divided by 2. So you can see over here in the red line, 4 is at 3, but now it's at 4 is at 1.5. We can look at other points here on the graph. Maybe see 5 is at 2. Well, 5 was at 4 over on the red line here. So it's just every y point is cut in half. Let me clear this out so we can see more. All right, what happens to h of x, all right, as x approaches 2? So let's talk this. As we get closer and closer to 2, we get closer. Basically, there's a jump. So there's a vertical or asymptote or a jump. We might call these poles too, but that's when we get into later. But there seems to be a jump because on the left side, it's going down towards infinity. On the right side, it's going up towards positive infinity. So what is the effect of the graph of f of x when dividing x minus 1 by x minus 2? All right, and we're going to compare that to what we did. Well, okay, if we look at all these answers here, let me get rid of the blue line here. What we're doing here is, like, if we seek every point, we have different slopes. All right, so we got 0 is at -1, and this one 0 is at 1.5. Okay, because we could take our answer that we're getting here and we were dividing it by, well, whatever 0 minus -2 is. So if we take -1 divided by -2, it is equal to 0.5. Let's look at some other points here. Like, we know 5 is at 4. Over here, 5 is at 1.333. So every single time we're dividing it by a different number, because we'll take that answer that we got here, 4, and then we divide it by whatever 5 minus 2 is, 3. All right, if we go further on down the road, okay, here, 7 goes to 6. All right, so we'd have 6 in the top, and then 7 minus 2 is 5. So we probably get something here at 7 over 5, which is 1.2. It's kind of hard to see here, but yeah, There we go. So every single time we're dividing it by a different number. All right. So what we're going to do now is to see like how can we actually figure out where those asymptotes are without using Desmos. And there's a way we can do that. All right. So zooming these notes up here. When we want to rewrite a problem here to look more like a relation or rational function here, a 1 over x, we have to use long division. And when we use long division, we get something over x minus h plus k. You can kind of think about this here. The h and the k are going to be the center of that asymptote there that we can find. So we use long division. So we take 4 divided by x minus 3. And if you remember here, all right, we just look to see the x. What do we have to multiply x by to turn into 4x? It's 4. And then we go ahead and distribute it out. And then we have a remainder. So the answer is 4 plus our remainder here. So this 4 is going to be our vertical shift upwards. And in the remainder, it's, remember, the opposite here. All right, and so we can move over. Then now the 12 here that we get is the stretch factor of 12, which really, it's nice when we're plotting points, but the key part in this section is if you can identify the vertical and horizontal asymptotes. So let's try to do this one here without using Desmos, and then we'll use Desmos to check our answer here. Okay, so if we were going to try to figure out what does this graph look like? All right, so first thing we would do is we would take 6x and we divide it by 2x plus 1. All right, so what do we have to multiply 2x by to turn into 6x? We'd have to multiply it by 3. We would distribute that. We get 6x minus or plus 3. All right, we're going to subtract now. 6x minus 6x goes away. We have 0 here. If you want to put that space filler, you can. Minus 3 would be a negative 3, and that's our remainder. So the equation could be changed or rewritten to 3, which is our answer, plus our negative 3 over x, or 2x plus 1. Where's my eraser? Okay, so let's talk about our vertical and horizontal asymptotes. So our vertical asymptote and our horizontal asymptote are found by our h and k. All right, so if you look here in our example, you can see that plus 3 that was on the outside there, that was the number on the outside, and so we have another one here. So that's going to be our vertical asymptote. So x equals 3, which we can found by this number here. Our horizontal asymptote is going to be found here. Now, normally it is just, you know, x minus h in the denominator. So if we wanted to make this a plain old h, we have to go through and try to divide this by 2. And so we could change this to, we divide this by 2, it'd be the same as x plus 1/2. Okay. And so that means our horizontal asymptote is at y equals negative 1/2. Just using this previous example above here. Okay, let's see if we actually did that right by checking out Desmos. So we're going to type the equation in. 6x divided by 2x plus 1. Okay, so if we look here, we said, oh, my mouse is going crazy. We guessed that we had a vertical asymptote, or no, a horizontal asymptote at y equals 3. That was the number on the outside. And then a vertical asymptote at x equals negative 1/2. All right, so remember our vertical asymptote comes from the number on the outside. Our horizontal asymptote becomes basically by setting the denominator equal to 0. I'm trying to figure out what that does. Okay. So next, let's try that again. Let's use long division to rewrite this here and talk about what we can have. So another try here. If you want to pause this, try this one on your own. Do that. If not, I'm going to start this in 3, 2, 1. All right, so we got to take x minus 6, and we're going to divide x by x minus 6. So what do we have to multiply x by to turn it into x? We have to multiply it by 1. When we distribute that, that just becomes x minus 6. And then we subtract to get a remainder. I'm going to put a plus 0 to help me out here. And a remainder is going to be 0 minus negative 6. Okay, that'd be 6. So the equation can be rewritten to 1 plus the remainder of 6 over x minus 6. Okay, so let's remember the number on the outside tells us the horizontal asymptote, which is our y equals. So how much of a shift that is, that's 1. And then the vertical asymptote. I think the easiest thing to do to find out the vertical asymptote is just set the denominator equal to 0. That would be 6. Or if you have it simply here, it's just up. So when x equals 6, we have a vertical asymptote. So we think the horizontal asymptote is at 1. The vertical asymptote is at 6. Let's double check our findings on Desmos. Ready? So we have x divided by x minus 6. We guess that the horizontal asymptote was 1. Looks so good there. And our vertical asymptote was at 6. And you can see there, we got it set up. Okay, so basically we can have more complicated rational functions, but the how to use those or find them are very simple. It's just the same rules, even if we get something more complicated like what's about to be ahead. All right, so just as any rational number, we can always express the 2 as a ratio of 2 integers. So a rational expression is an expression that can be expressed by 2 polynomials, such as like p of x and q of x. The one thing that q of x just cannot ever equal 0. So a rational function is a function defined by a rational expression, such as an r of x, or rational function, is equal to p of x divided by q of x. So the domain of r of x is all the values of x for which q of x cannot equal 0. So that's a really, really fancy way of saying the domain is everything except for what makes the denominator 0. All right, so the domain is everything but where the denominator equals 0. Okay, so that's going to lead us to the next part of how do we find vertical asymptotes. What we have to do here is if we have a function, we have to look to see where the denominator equals 0. So when we have a crazier expression like this one here, x squared plus 7x plus 12, we're going to have to set it equal to 0. So whenever we're trying to find vertical asymptotes, or also known as discontinuous points, we have to set the denominator equal to 0. And so if we have a quadratic, we can factor that one. All right, and we can get 2 answers here. So one of them is x plus 3 and the other one's x plus 4. We set those both equal to 0. We can figure out that we have x equals 3 makes that denominator 0, and also x equals negative 4 makes that denominator 0, which means we would have vertical asymptotes there at negative 3 and 4. Okay. So when this comes, there's actually a couple things that could happen. So that is probably the easiest thing here. So there's 3 cases we have to look out for. So when we have to find vertical or horizontal asymptotes. All right, so that's vertical asymptotes, that's easy. How do we find horizontal asymptotes is a little bit tricky. All right, so the first case scenario is if we have, like what we have here, where the larger degree is on the denominator. If the larger degree is on the denominator, that means there's going to be a horizontal asymptote at 0. It kind of makes sense if you think about it here. So if we pick numbers for x here, like 10, this would be 10 over, or 10 plus 4 over 100 plus 1. So that's going to be like 14 divided by 101. And if we make this get bigger, we go to 100. That's 104 divided by 100 squared. It's 10,000 plus 1. So as x gets bigger, the bigger number even gets bigger and bigger on the bottom. So it's going to get closer and closer to 0. So case 1 for horizontal asymptotes is if the bigger numbers on the bottom, bigger degrees on the bottom, it's 0. All right, second case is what happens here if the larger degree is on top. If the larger degree is on top, there's no horizontal asymptote. It goes towards infinity or negative infinity, and that's all determined by something else that you'll learn if you take pre-calculus. Okay, so 2 cases so far. If the bigger one's on the bottom, it's 0. If the bigger one's on top, it doesn't exist. All right. All right, next, case 3. What if the degrees are the same? Well, if the degrees are the same, we can use long division here, and we can rewrite the expression like so. Now, what always happens here, if you look, we will actually look at our leading coefficients here, which is 2, and this is 1. And the answer, the horizontal asymptote, is always going to be equivalent to the leading coefficients divided. So 2 over 1 is equal to 2. All right, so let's try a couple of these here. We're going to find the vertical and horizontal asymptotes of each graph. Okay, so without using a calculator, but only just to check our answer at the end. So vertical asymptotes. The vertical asymptotes is where the denominator equals 0. So when does x squared minus 2x minus 8 equals 0? Okay, so this would be, if we factor this, we got an x, let's see, what 2 numbers multiply together? 8, negative 8, so there'd be x minus 4 and an x plus 2. All right, so that means we'd have an x equals positive 4 and an x equals negative 2. Okay. Now, our horizontal asymptotes, we're going to look at our degrees. We have degree 2 and degree 2, so it's the same. So we're going to look at our leading coefficients, which are 2 and 1. So 2 over 1, so that means we have a horizontal asymptote at 2. Okay, so let's check this out. We think there's vertical at 4 and negative 2, and a horizontal at 2. Okay, let's clear this out. Let's grab this. Okay, I'm going to clear this out, clear this out. Oh, I probably shouldn't have to, but we got 2x squared, complicated equation, plus x minus 9. All right, and we're going to divide that all by x squared minus 2x minus 8. All right, let's look. We said we had x equals, was that negative 2 was one of them? Oh. That looks good there. And we said x equals 4 was the other one. I'd say that definitely looks like a vertical asymptotes in the right spots. And then we also said y equal to 2 was a horizontal asymptote, which the one thing about horizontal asymptotes, vertical asymptotes never get crossed. This horizontal asymptote can cross, but what we're doing more is looking at the end behavior of the graph. So the graph keeps going to the left, it never crosses it. As it keeps going to the right, it goes closer and closer. All right, let's try the next one without a graphing or without the graphic calculator. Try it on your own if you would like. I'm going to start it in 3, 2, 1. Okay, so if we want to go ahead and try to find the vertical asymptotes, what we need to do is set the bottom equal to 0. All right, so this isn't a quadratic. Well, it is technically a quadratic, but we don't see our like a, b, and c to try to factor this. We could, but we can always just do normal things to solve it. We could just add the 12 over, and then we can divide by 3. And then we could take the square root. Now, when we take the square root, we have to remember to do a plus or minus. So we actually get a positive 2 and a negative 2 would be our vertical asymptotes. Our horizontal asymptotes is where we look at the degrees. Okay, they're the same. So we're going to look at our leading coefficients, 1 over 3. And that just is simply 1/3. So let's double check this here. Let's see, I'll leave that up. Let's change this. Okay, we got x squared plus 5x plus 4. All right, and then the bottom we have a 3x squared minus 12. All right, and we said, okay, we have one at negative 2, one at positive 2. We said y equals 1/3. All right, let's check this graph out. How's that looking? I'd say that looks really good. Okay. So let me clear this off. When it comes down to this here, when we're trying to graph a function, what we want to do first is look to see if we have any vertical asymptotes. And you can see here, in this equation here, we set the denominator equal to 0. Then the next step is to find the horizontal asymptotes. And so we draw our dotted lines as such, like if we're trying to do this on graph paper without using the graphing calculator. Then what we're going to do here to graph the function, we just choose some x values to determine, like after we make our grid, because what ends up happening here, we have our vertical asymptote and our horizontal asymptote. We're going to pick a value to determine, well, is our graph going to be above it or below it? And then which region is it going to be? So we just have to pick an x value in between these areas here to figure out where they're at. So let's try to graph this one here without using a graphing calculator, and then we'll just kind of double check if we did this right. All right, so if we want to find our vertical asymptote, we set the denominator equal to 0. All right, so that means we have a vertical asymptote of x equals -8. So I'm going to draw that in right here. All right, next, we need to find our horizontal asymptotes. And if we look here, the degrees are the same. So our horizontal asymptote is 4/1, which is just 4. Okay, so you can see we basically kind of make a T shape. Next thing we got to do is like to find the points. Is the T going to be above or below here? Where is it going to be? Which one? All right, so I'm going to pick a number to the left of -8. I'll pick -10 because that's kind of nice to do. So if I was going to find f of -10, I'm going to do 4 times -10 plus, or -3 over -10 plus 8. All right, and so f of -10. Let's see, that is -40 minus 3, so that's -43 over, this would be -2. And let's see, that's like -21, right? Or no, -21.5. Okay, so that means we are definitely down here below. Did we do that right? Yeah, -43. Wait, no, that's positive. Divided, okay, so we're up above. Okay, so that means that at -10 we're above. So that means we're going to have a graph that's above that line there. And it's going to be curving like that boomerang like we see before. All right, next, okay, let's pick a number to the right here, see where that is. So let's pick a number. I like 0. 0 is an easy number here to do. What's 4 times 0 minus 3 over 0 plus 8? That's -3 over 8. Okay, -3/8, which is, right here. So we'd have a graph below. So we probably have a graph that looks like such. All right, let's see on Desmos if we did that right. Just gonna kind of clear this out. We got 4x minus 3. We're going to divide that all by x plus 8. All right, and if we look here, we have it above, below, so we were right with our guess. And then we can see here with our vertical asymptotes, we have the vertical asymptote at -8 and the horizontal asymptote looks like at 4. So Desmos is just going to be the tool we use not to get our answer, but to just double check. Because who knows, we might not be able to use Desmos on part of the test. All right, so let's try this one again here. How do we graph this? So if you want to try this one on your own, feel free to do that. But I'm going to do this. So pause the video if you want. I'm going to do this in 3, 2, 1. All right, so vertical asymptotes, where the denominator equals 0. And that is at 1. Okay, so vertical asymptote at 1. All right, our horizontal asymptote. If we look here, the degrees are the same. So it is going to be a 3/1. That's just 3. All right, so where is the graph? Is it above? Is it below? Or is it above and then below? We don't know. What we have to do is pick points. So let's pick a number to the left of this. I always like 0 if I can pick that. All right, plug in 0. What's 3 times 0 plus 2 over 0 minus 1? All right, that would be 2 over -1. All right, that's -2. So that means at 0, we're at -2. So that means all of this graph has to be below. It makes a boomerang shape. We could get better points here, but we just want to know we have the curve below the graph. Yeah, it definitely probably looks better there. We can pick other points if we want to get more accurate, but we just want to know where's the graph, what region is it? All right, now over here, is the graph below here or is it above? We have to pick a point to the right of our vertical asymptote of 1. So I'm going to pick 2. That's a nice easy point here. Plug in. So what's 3 times 2 plus 2 over 2 minus 1? All right, that's 6 plus 2, that's 8 over 1. All right, that's 8. So that is at 2 is at 8, so that's above. So we would have a graph starts below and then goes above. Let's double check that here. (3x plus 2), and we divide that by x minus 1. Yep, it goes below, starts above, and where vertical asymptote matches. Okay. Let's talk about some other things that we could have here, some more complicated. So sometimes we can have factors here where we get 2 vertical asymptotes, which happens, and then we also get a horizontal asymptote. And what we're going to have to do is when we get multiple regions here, in this case we have 6 regions, we have to plot points all the way in between to get some of those values, to notice those. And this is where a table or a graph really becomes more important. Okay. So let's talk about this here. Let's identify some of these asymptotes. All right, so you know what I'm going to do here is I'm going to full screen this as much as I can. Okay. And I'm going to have to just use the graph. I'm going to have to write the equation over here. What do we got? We got x squared minus 5x plus 6 over 2x squared minus 10. Of course, it'd be something like that. Okay, so let's do this here. To find our vertical asymptotes, we're going to have to go through set the bottom.
Good morning, Lancaster High School. We are in activity period this morning. If you are a junior and
okay, so let's get this going. We set the bottom equal to 0. And so we're going to just kind of solve this for x. So we'll add the 10 over. We'll divide by 2. All right, that'd be 5. And when we take the square root, we just get square root of 5 doesn't come out nice. So we got a positive square root of 5. We also have a negative square root of 5. All right, so on a graphing calculator, we just got to kind of figure out what that number is. So the square root of 5 is about 2.24. All right, so that means, okay, just after 2, I'm going to put a vertical asymptote. Man, that is a wonderful dotted line I just drew. And then we also have one at negative 2.24. Okay, horizontal asymptotes. All right, horizontal asymptote, we look, okay, degrees match. Hasn't been tricky yet. So it's just going to be leading coefficients is 1, the other one is 2, 1 over 2 is 1/2. All right, so we got a graph that looks like such. Okay, so this is where we'd want to go through and pick multiple points to figure out, okay, where is the curve going? And so, all right, what we would do here is like, sorry if you can hear that kid, pick some numbers and we're going to plug them in. Now, this is also kind of where I would expect you guys to, you know, use a calculator for this point. I'm going to really be judging you guys on whether you guys can get the correct vertical and horizontal asymptotes. And then after that, I would assume you guys would want to use a graphing calculator because we can get a table real quickly with that. All right. Now, you could do this without a graphing calculator. It's not impossible. You could just pick points and plug them in, plug them in, plug them in. But we ended up getting, I mean, especially this one here, that's kind of a crazy graph. Is that right? Let's see if we did this right. If I say x equals, and then I did the square root of 5, the square root of 5. Oh, hey, that looks really good. And then if I did another one, x equals the negative square root of 5. All right, so we definitely have those here. And then we said y equals 1/2. All right, it looks like we definitely have our vertical, horizontal asymptotes matched up. Looks like the graph starts low, goes up. It starts at the bottom, does a wiggle, and goes up. And then the bottom starts down, goes over there. Okay. So when it comes down to this here, we're always trying to find vertical and horizontal asymptotes, but there is another catch. And let's talk about our worksheet here. All right, holes and poles. Okay, so this is going to be the worksheet you guys work on. Poles are really easy. Poles are asymptotes. So where the graph approaches but doesn't, like, so you can see here, we have a simple equation. We don't have it already set up. So we have our denominator here, which will tell us the vertical asymptote. And then this K number out here tells us the horizontal asymptote. Pretty easy. Same thing here. Now, holes. Holes are a little bit different. So I'm going to do this one. So you might look at this one here and think, okay, we would have a vertical asymptote when the denominator equals 0, right? Because that's what we've said. We have a vertical asymptote whenever the denominator equals 0. So we should have a vertical asymptote when x equals 2. So that means we should expect a graph, a point, when x equals 2. Well, let's look at this here. If I take x squared, start now, x squared minus 4, and we divide that by x minus 2, we don't see a jump at all. But we said there's got to be some type of problem here at 2, right? Because the denominator can never equal 2, otherwise it's 0. So let's zoom into our graph here. Here's 2. Oh, looks like there's a point at 2, 4. Let's keep zooming in here. Now watch. This is kind of crazy. And you can actually kind of see something as I hover over it. That gets white. Let's see how far I have to zoom in here. I'm just zoom in for the heck of it. Keep zooming in. Still looks good. Uh-oh, what's going on here? Oh, there it is. So there's a problem here. There's a hole in the graph. Now we have to zoom in super, super far to be able to find it. And I'm basically to the point where we go through here. All right, so not all discontinuous points, and remember that's where the denominator equals 0, is a vertical asymptote. Sometimes it can be a hole. All right, so you have to use a graphing calculator to find out where that hole is at, and then use that other point. But okay, we have a hole at 0 or at 2, 4. So when x equals 2, there's a hole. We'd still say the domain is, x cannot equal 2, and then the range is y cannot equal 4, and we can get that by actually looking at a graphing calculator. And then we're going to go ahead and just kind of draw. This would be a straight line graph. Now let's talk about how we can figure that out. The reason why we can determine that is because the top, yes, we know the top equals 0, or the bottom, that's where it equals 0, but the top we could factor to this x plus 2 times an x minus 2. If the bottom can ever cancel out, that's going to be a hole. If it cannot cancel out, that is going to be a pole. And that's something we're going to be working on with all of our worksheets that we work on here. So you can see here, there's going to be another hole here because you could factor the top. The top factors 2n x plus 4 times an x minus 3. All right. That 3 cancels out, so that would be a hole, not a vertical asymptote. And then this one here is an example of holes and poles. And if we look at that, the reason why that is because we could factor the bottom here, and the bottom has a couple mistakes in it. We have, let's see, that'd be an x minus 3 times an x minus 1. So there is, if we look at this here, there is a hole when x equals 1, but a vertical asymptote, a pole, when x equals 3, because that doesn't cancel out. And then we got some crazy graphs here as well. Let's see. So you can see some of these here as well. You'll have to look to see, okay, what's our denominator? Can anything cancel out? All right, here, can you cancel out a 1 from the top? Can you cancel out the 4 from the top? No, you cannot cancel those out. So they're asymptotes. Over here, could you factor this and maybe cancel out that? Okay, so if you can, it's going to be a whole. Over here, is there anything you can cancel out? If not, it's going to be an asymptote. So we're going to spend some days on here, making sure we understand the graphs, doing all right with this, and then you guys have your CYU. Okay, so that was a lot of the notes, but we'll be working on these graphs for a while. You guys have a great day. Always check your work on Canvas, and I will see you next time. Adios.